Hello everyone. Today I'm going to talk about PE-SpGEMM, bandwidth optimized parallel algorithm for sparse matrix multiplication using propagation blocking. My name is Zhixiang. I graduated from Indiana University. Jules and David are with IBM Research. Azad is my advisor. He is an assistant professor at Indiana University. First, a little bit overview. Sparse matrix multiplication is getting increasingly important in modern days. It is an important kernel in many domains. For example, in graph analytics, SpGEMM is used in between centrality, clustering coefficients, triangle counting, colored intersection search. In scientific computing, SpGEMM is used in algebraic multi-grid, linear solvers, many machine learning tasks like dimensionality reduction, spectral clustering, and Markov clustering also rely on a very efficient SpGEMM algorithm. So it's not a surprise to see that there are many algorithms out there. SpGEMM is primarily memory bound, so the data access pattern can play a significant role in the performance. In this work, we are categorizing SpGEMM algorithms based on the memory data access pattern. If we see an algorithm only has stream access, in other words, data is read or written continuously, we would expect this algorithm has a very good performance. However, if an algorithm has random memory access, it's going to lose some performance. Specifically, we are going to discuss two different algorithms. The column-by-column algorithm, which has stream access to the one of the input and the output, but not the other input. And the outer product algorithm, which has stream access to both input, but not the output. Let's take a closer look at the column SpGEMM algorithm. As per the name, this algorithm generates the result column by column. Every iteration, it picks a column from the matrix B and multiply all the non-zeros with the corresponding columns from matrix A. And then you can use different strategies to merge the data to yield this column. So you see, the axis of B is continuous. However, the axis to the A is random. We have to match the index here. And we have fetched the data multiple times. Outer product SpGEMM is different. Every iteration will pick a column from matrix A and multiply it with the corresponding row from matrix B. Because we are doing outer product, so it's going to generate a rank 1 submatrix. After we continuously doing so until finish reading all the A and B, then we sort and merge to convert the expanded matrix C hat into the final result. So you see, we have stream access to both input, but the access to the C hat is not non-stream, and we have accessed the C hat multiple times. The work of us is primarily answering a few questions. First, given two input matrices, A and B, and given a system, what is the best performance attained by any algorithm? What is the best possible performance that a given algorithm can attain? Second, given the observed performance from an algorithm, can we explain why the best possible performance may or may not be achieved under a performance model? Finally, can we develop an algorithm that always achieves the performance predicted by the Roofline model? Before I get to the model, let me introduce two very important concepts. The first one is compression ratio or compression factor. It is the total floating point operations to number of non-zeros in the result. The higher the CF is, the more flops will be merged during multiplications. Another one is arithmetic intensity. AI describes the capability of how much work you can do given a certain amount of memory movements. More formally, AI is a ratio of total floating point operations to memory read and write. Because we are multiplying two matrices, so the minimum requirements for the memory movements is to pull the A and B out of the memory and write the C to the memory. So the AI should be smaller or equal to CF over B. Given a machine with beta bandwidth, we can assume that the peak performance flops should be smaller than or equal to beta times CF over B. However, experiments have shown us that no existing algorithm is able to achieve this number, not even close, and we need a more realistic model to help us analyze the algorithms. Let's recall the column-by-column SPGEMM. During the multiplication, we do only access matrix B once, but we access the matrix A multiple times, so we put a CF here. And AI of column-by-column SPGEMM should be greater than or equal to CF over 2 plus 2CF. Similarly, we generate a extended matrix C head, and we access it twice. So AI of outer SPGEMM should be greater than or equal to CF over 3 plus 2 times CF. Consider Edelsohn model, which CF is equal to 1, and we are using COO format to represent the non-zeros. Each tuple is 16 bytes. So we found our calculation, the AI of column SPGEMM should be greater than or equal to 1 over 48, and AI of outer SPGEMM should be greater than or equal to 1 over 80. Assuming we are running on an Intel Skylake system with single-socket memory bandwidth equals to 50 gigabytes per second, we can draw a Roofline model here. So you can see theoretically, column SPGEMM should perform better than outer SPGEMM. Our model suggests that the column-by-column algorithm has a theoretical peak performance of around 1 gigaflops per second. But in reality, based on our experiments, even state-of-the-art algorithm implementations can only get half of the peak performance here. The most important reason behind this is when we multiply the non-zeros with the corresponding columns from matrix A, we are randomly accessing them. The latency cost could be huge if the matrix is large and sparse, which cannot be fit in the cache. It may not be possible to avoid the irregular data access problem in column-by-column SPGEMM. This is where our new algorithm comes to rescue. The new algorithm is called PE-SpGEMM, which is based on ESC formula. The E here stands for expand. In this phase, we are going to do the multiplications and create unmerged tuples. S here stands for sort. We sort tuples using row ID and column ID as keys. Finally, we compress. We merge the duplicated tuples and yield the final result. Underlying the algorithm is the order product formation, which enables us to enjoy the stream input access. We briefly discussed before that order product is extremely hard to organize intermediate results. To solve this, we applied a technique called propagation blocking, which was introduced by Professor Beamer in the SPMV problem. Now the question, what exactly is propagation blocking? Let's take a look at the example here. Assuming we are running on a machine where the cache line is 64 bytes, and each tuple we use to represent the COO format is 16 bytes. In this particular iteration, we're going to multiply the third column with the third row, and we have created 4 arrays to store the intermediate result. Without the propagation working, these two guys will generate a tuple which is going to go to the row 0, and these two guys will generate tuple which is going to go to the row 1. You see, they are not in the same cache line, and for this iteration, we are using 2 cache lines, each with 50% of utilization. This may not seem a lot, but when our matrix is getting larger and sparser, we are basically writing data to random place in the memory, and we will have a very poor cache line utilization. Unlike cache blocking, which partitions the input until it's fitted in the cache, propagation blocking partitions the data transfer during modifications. So in this case, we have created 2 bins instead of the 4 arrays. And bin 0 will block the propagation, which was supposed to go to the row 0 and row 1. Similarly, bin 1 will block the propagation, which was supposed to go to row 2 and row 3. So all the data, all the tuples can fit in bin 0, and we have 100% cache utilization. In our implementation, we actually have used 2 different types of bin. We first write the data into small local bins. Once a particular small local bin is full, we move all the tuples in this bin to the corresponding global bin. So the goal of the local bins here are used to improve the access of the C head. You can see here a large local bin will help improve the bandwidth, but we need to make sure the number of bins will not be crazy. So and the total bins can be fit in the L3, L2 cache. On the other hand, the global bins are the ones that are actually storing the intermediate tuples, which will be later used in the sort and merge. We also need to make sure that each global bin can be fit in the cache, so we can enjoy the cache speed in the sort. After the expand phase, the expanded matrix C hat is stored in the COO format, partitioned into several bins just like this, and then we sort use the in-place radical sort. Specifically, we apply the 2 optimization strategy. The first one, we concatenated the row ID and column ID to fit in an 8-byte integer key, which will enable us to use fewer passes to get the array sorted. And we also adjusted the number of bins to make sure each bin is sorted in the cache, and we can enjoy the cache speed. For the compress, we apply the 1-pass 2-pointer method. The sort and compress is pretty straightforward. I enjoyed you to read our paper if you would like to see the details and optimization we applied. To better summarize the algorithm, we have 4 examples here multiply 2 4x4 matrices. In this case, we use 2 bins. So the tuples with row ID 0 and row ID 1 will go to the first bin, and tuples with row ID 2 and row ID 3 will go to the second bin. We use local blockers and global blockers to saturate the bandwidth here. Then we use a radical sort to sort the tuples and use the 2-pointer 1-pass merge method to remove the duplicates. Finally, we convert to the matrix to the CSR format. Finally, I'm happy to share some evaluation results. We evaluated algorithms extensively on 2 modern systems. The Intel Skylake system we are using has 24 cores and 2 sockets with 33 megabytes L3 cache. From the stream benchmark, we can know that from a single socket, our system is able to do 50 gigabytes per second. PowerNet machine has a smaller cache but higher memory bandwidth. We evaluate the algorithm comprehensively on both synthetic matrices and real matrices from the sparse matrix collection. We evaluate against the state-of-art SPGEMM algorithms. These figures show the evaluation for the synthetic matrices. For the ER matrices, the PE-SpGEMM algorithm runs 30 to 40% faster, and we are able to get around 45 gigabytes per second. For the RMAT, which has a larger compression ratio, we applied a two-way load balancing technique to mitigate the strong inverse power law effects. We are still able to outperform the others, but the memory bandwidth is slightly lower than the ER. The figure describes the performance of SPGEMM algorithms when squaring real matrices on single socket of the Skylake server. As you can see, the memory bandwidth we got is relatively stable between 47 and 55. And performance is relatively stable too. We sorted the matrices in the order of the compression factor. PE-SpGEMM is generally doing better than peers, except the last two. In these two cases, the compression factor is higher than 13. In these cases, the hash algorithm definitely has a better advantage. Similar performance is observed on the PowerNet machine. In this experiment, we were using 20 cores and 20 threads with higher memory bandwidth but smaller cache and smaller number of threads. It's interesting to see that PE-SpGEMM is still doing better than the others, and the performance remains relatively stable too. We did many other experiments in the paper. I encourage you to see these experiments. Well, this is the end of the talk. Our discussion section will be held between 11:30 and 11:40, July the 15th. Thanks to everyone for listening my talk. I'm looking forward to see you there.